Welcome back to the Impact Storytelling Podcast. I'm your host, Sabine Pritz Bay, Ocean Conservation Storyteller and Organization Director. Today, I'm joined by Mara Rosmann, a marine scientist and PhD researcher at Alfred Wegener Institute, Bremerhaven. Mara's journey into ocean science began with biology studies in Austria, led her to biological oceanography in Germany, and eventually took her to some of the coolest and remotest places on Earth, the polar oceans. Her research focuses on how carbon moves through the ocean along the East Antarctic margin, especially in regions where warm, deep waters meet ice shelves. By joining ship-based expeditions in the Arctic and using natural trackers like radiocarbon, Mara helps us better understand how Antarctica and the Arctic influence Earth's climate, and how these systems may be changing. I'm excited to explore her journey, her work, and what it all means for our planet. Welcome to the podcast, Mara. I'm delighted to have you here. You began your academic path studying biology in Graz. Was there a moment when you knew marine science was the direction for you?
First of all, thanks for having me. It's a pleasure. And I actually thought about that several times because this is something people usually ask, but I have to admit I don't really know when that happened because I had the pleasure that I got in contact with marine science very early in my life because through my father, who is operating this marine biological station in Croatia. So it was always kind of normal for me to be in touch with it. And I actually also never really thought about to really go that academic path by my own. But I actually wanted to become an actress, but that failed. And then I started my biology studies in Graz. And I realized that I'm missing something because I was so used to marine sciences all the time. And I thought about what could it be. And it never really occurred to me that it could be that I'm just super interested in the ocean and into marine science. And at some point I met a student in the marine biological station in Croatia where I've been working for several years in summer, and he been telling me about a GeoMar. And this is an institution in northern Germany. And then he told me what kind of studies they do there. And I didn't even know that it exists. He was talking about oceanography, biological oceanography, chemical oceanography. I didn't even know that is a thing. And that there is a master studies also called that way, biological oceanography. And that was actually, when I looked it up, I thought, oh my gosh, this is exactly what I'm interested in, because I was always super interested in meteorology and in like big processes and big circles. And this studies basically combined everything I was interested in. And then I thought, this is actually also the motivation for me to finish my bachelor, because I lost a little bit of motivation, I have to admit. And then I saw I actually have the opportunity to apply for these master studies. And I think that was the moment when I reconsidered and thought maybe this was actually my passion all along. And it turned out to be true.
Amazing. Yeah, it's great how many different people from different studies you can meet at the Meeresschule. And your master thesis took you to the Humboldt upwelling system in the Chilean coast. What exactly did you research there?
First of all, I took this thesis opportunity because I was asked to join the cruise. So one of the working groups I was doing like a student assistant job a few hours a week was asking me if I am interested into going onto a big research cruise. And I was like, oh my gosh, of course, this is the dream. And then they told me it's going to be in the Humboldt upwelling system, which is really closely connected to these El Nino and La Nina events. Probably everybody or a lot of people have heard of, also from media, because it affects also our local climate and weather in Europe, Austria, Germany, wherever. And I told you before that I was also always interested in meteorology and stuff. And I thought, wow, okay, this is, first of all, I can go on a research cruise. And then I can kind of combine these huge fields like the atmosphere and the ocean, because this is especially important in the Humboldt upwelling system, where these events have their major impacts. And I was then joining the group of marine biogeochemistry on that cruise. So this is a very long word, but it actually really combines all of these disciplines. Biological oceanography, it really combines a lot and looks into big element cycles in the ocean. And this is also what I was interested in. And we were mainly looking in this working group into the biological carbon pump and its efficiency. This is probably maybe a little bit of a cryptic word. It was also to me in the beginning, but it basically describes how the biosphere, so all kind of living organisms in the ocean, are able to capture carbon in shape of CO2 from the atmosphere, store it in their own organic matter, and then transport it through the ocean in form of dissolved organic carbon or bigger particles, which is particulate organic carbon, and that gets either sinks down by its own or gets transported by ocean currents. And this is very important because the ocean has this buffer function for our climate. So if we have a lot of CO2 in our atmosphere, ocean is able to take it up and transport it, ideally to the deep ocean, and store it there. So everything we kind of mess up and put out there, the ocean is able to a certain extent, unfortunately, to take up and store, for example, in the deep ocean, and even bury in sediment where it stays for geological timescales. So we're talking about millions of years. This is the best case scenario. And I was looking into a little tiny link of this biological carbon pump because it's super complex. And I was looking into one specific particle, which is called transparent exopolymer particle. This is produced by microorganisms, so by phytoplankton in the ocean, which are able to take up carbon and transform it into this organic matter. For example, this transparent exopolymer particle. And this, people believe that this has the potential to transport a lot of this carbon into the deep ocean, because the particles can get very big and they also contain a lot of carbon. So if these particles then also can sink down, they have a high potential to transport carbon from the upper ocean to the lower ocean, and maybe also store it there for a long time. And this was what I was looking into in my master's, yeah. And I also had the opportunity to go there by myself, take all samples by myself, and this was, very, very impressive.
Sounds like an amazing opportunity and a really good time. I was wondering, when you just explained everything, so with all the deep sea mining plans and constructions they want to do down there, is not everything gonna be disturbed and could have really bad consequences?
Definitely. I mean, I'm not, this is actually a hot topic in marine sciences, as you probably know, because it's right about to start, and it already started in a commercial way. And colleagues of mine are actually working on that. And I mean, in general, we have to think about an ecosystem, space on Earth that needed millions of years to develop. And then we kind of destroy it in a matter of seconds, minutes. That fact in general, that doesn't sound really scientific now, but that fact in general tells me, okay, that has to have a huge impact, because there is a reason why it takes millions of years to develop. There's a lot of energy in it, and big processes and end members that are very important. And we it's the same as a tree that needs decades to grow, and we cut it down in a minute. And I think I don't actually know, and I think people still having a hard time to actually define the importance of, for example, these metal-rich manganese nodules people want to harvest. I think people still having a hard time to actually define the role of them in the deep sea, for example, ecosystem or element cycles. I think this is still very complex and still very unexplored. Why? It is a pity that we don't have the time to do that. I mean, people try, but we're kind of running against time. But one of the problems that is a little bit of shorter time scales is that when these machines are kind of plowing, is it the right word? Plowing through the ground. So they kind of disturb the sediments, and huge sediment plumes kind of get resuspended and fill up the water column. And we actually don't really know what in these sediment plumes is. It could also be like very toxic, for example, methane or fouling gases that naturally develop in sediments. But we kind of bring them into the water column and they get distributed via currents. And on the one hand, sediments bury complete ecosystems when the sediments settle down again. And also all of these fouling gases get distributed. So we definitely already know that there are short-term implications for all the deep sea ecosystems, which are usually untouched down there. Regarding element cycles, I think we cannot know because we need so much more time to look into that. But in my opinion, it has to have implications because of the first thing I said. But yeah, I think people still having a very hard time to actually, say something about that. But short-term implications for ecosystems, 100%. Unfortunately, yeah.
Yeah, it's sad like always. They're just looking at the money they could get and not trying to research everything before, make sure it is safe for the environment and also for humans.
Yes.
But when did the polar regions first enter your imagination as a place to work and to research?
Actually, also credits to my father. So when he was in his studies, so he studied zoology at the university in Graz in Austria, and he joined this research cruise on Weiter Herwig 3, very traditional name for a ship, which is a fisheries research vessel that usually does research around the Baltic Sea and the North Sea, but once a year also goes to Southeast Greenland. This is not really the Arctic yet, because people always think when it's about Greenland, oh, it's already Arctic, but it is actually not. I mean, Southeast Greenland is huge. It extends through many latitudes. Southeast Greenland is close to the Arctic, I would say. But it feels like Arctic. You already see like icebergs floating from higher latitudes down, and you have the chance to see them. You have the chance to see marine wildlife, which you associate to the Arctic. So it feels like Arctic. And he went there, I'm not 100% sure, I think in 2008 maybe. And he came back with a lot of pictures and with a lot of stories. And I was 13, I think, or younger, I don't know. But he came back and he showed me all of this. And he also collected a lot of stuff they kind of, which was kind of bycatch during their research, like little stones that were collected from the seafloor and stuff. And I was looking at all of that, and that was, of course, crazy. I couldn't really imagine where that was coming from, like from the Greenlandic shelves from 200 or 300 meters. But this was the first time I got in contact with polar research. But that was back in the times when I wanted to become an actress. So I didn't really think about it a lot. I just thought, wow, my dad is cool. That's amazing stuff. It kind of does something to me. It's super exciting, but I never thought about doing that by myself. And then when I did my bachelor's in biology in Graz, he actually gave another presentation about his expedition to the Arctic. I think it was just like an evening lecture at the university, and I attended it, and he showed these pictures again. I already completely forgot. And then I kind of related a little bit more to it because I was already studying biology. And I thought, oh my gosh, this is what people actually do. This is what people can actually do. This is like a profession. I think that was the moment where it first came to my mind. but it still was super far away. I still thought, yeah, for me, no chance. How could I get there? And yeah, then the whole thing with no, actually, then I thought I want to be part of that cruise too. And then I randomly wrote this expedition leader that changed already. It was not the same back then when my father did the expedition, because this is a yearly expedition, so it's a time series. They go there every year for 7 weeks and try to kind of estimate the fish populations there. And I just randomly wrote that expedition leader, and I thought, yeah, I would just write a mail, ask if I could join. He probably said no, and then it's done. And I wrote him a mail, and he just said, yes, of course. And I was like, what? It's that easy? And this is actually something for other people who are listening. It actually works like this. So you just write people. This is basically where I got today, that I love to talk to people, that I love to write people and be in contact with people. And he just wrote, yes, of course, it happens to be that we have a spare spot for you, and we can go. Next year, October, you are on board. And yeah, it actually, unfortunately, in the end, we went a year later, because I was there and the ship engine was completely broken down, and I was stranded in Bremerhaven for 2 weeks. And then they canceled the cruise. That happens actually not quite often, that they cancel cruises. That actually rarely happens, but it happens a lot of times that these ships have problems if they're already really old. But a lot of them are being replaced at this moment, actually, in the German research fleet. And yeah, then I went back home. But next year, he was really behind me for me to join again. So he was suggesting me as a participant again, and then I could join, and it was amazing, and I was completely hooked. And this is the case for everyone I talk to who has been to the Arctic or Antarctic, that you are hooked from the beginning. I don't know if you have been to the Arctic or Antarctic.
Yeah, I've been in the Arctic last month. But with a orca researcher in Norway.
Oh, wow. Okay, yeah, so I guess you're hooked too.
Yeah, it's really, really cool.
Yeah, it's just a really magical place. Like, not even talking about research, but in general, it's such a privilege to be there. And yeah, it's such a magical place, and I was completely hooked. And then I started my studies at GeoMar. And at GeoMar, this is this institute in Kiel with a huge focus on geosciences and geophysics, so seismics and stuff like this. There was not really an opportunity to link to polar research. I mean, there are some, but they are very sparse. And then a colleague of mine told me that he's been studying in his bachelor's on Svalbard. So it's this little group of island that belongs to Norway and is really high up in the Arctic, actually. So there's actually this university center. You probably know it, the University Center of Svalbard. And then I thought, oh, this could actually be something. I can just apply for courses there. And I still need to fill up my schedule with some courses of my choice. And there are these block courses where you can apply for, and then they last for 6 or 8 weeks. And I applied for that and got a spot on the first course, and then I went there again. Then I went there again. As I said, it really hooked me. The first course was in cooperation with the Technical University in Trondheim, which was really impressive because there were a lot of scientists and technicians coming with huge devices and sampling tools, and we were doing a huge campaign in Kongsfjorden, which is a little bit north of the fjord where the main university center lies. So where people just go if they are kind of invited. So I don't know how I got there. I ask myself that every day. I don't know how I got here, but it just happens. And we did this sampling campaign where we're looking into optics, actually, also associated to biology. So we were looking into different pigments of phytoplankton, and they had these drones. They even like launched this satellite for this project, and I was for the first time in touch with like these high-tech systems they use to observe our ocean like on a large scale. And that was super interesting. This was also the first moment where I thought, okay, all the techniques behind are actually also really, really interesting. And all the technicians developing these systems, they have my greatest respect. It's crazy what we can do nowadays. And the next year I was on a ship when I was doing the chemical oceanography course on Svalbard, which was also super impressive. We went through all of the fjords, and I was getting my first ice core. So there's actually also a picture of it, where I'm standing on the sea ice, and back then it was manually. On my latest expedition, I realized that there is also like an opportunity to do it like with a little engine, but they put us on the ice with just this manual ice core. We really had to screw in this thing to get our ice cores, and this was also my first time standing on sea ice, and that was super impressive. And I mean, I was already in love with polar regions then for a very long time. But I was still not in love with the academic pathway. So I didn't know how that goes hand in hand. And as I told you before, I was doing my master thesis actually in subtropical regions, and then I finished my master, and I also actually thought, okay, now it's over. I somehow need to find something else, because I was not a big fan of the academic system and all of this publishing pressure and this like elbow culture. I don't know how to describe it better. But then I tried to. I went back to Graz, and I tried to somehow extend my network with the polar researchers there, because I thought maybe I can get sometime a technician position or whatever. I don't know what I was thinking, but I went back and I tried to reach out for the people who are doing polar research. And then actually the time when I back, I discovered that Austria kind of announced that they're going to have their first polar research station like in the history of Austria. And I was like, what? This is happening, and this is happening now. That's kind of crazy. And it's this research station in cooperation with Denmark in the Sermelik Fjord in also in southeast Greenland. A little bit higher than I was with the ship, but in Sermelik Fjord, it's a huge fjord system with huge calving glaciers. And I was reaching out to these people, where I realized, oh my God, the polar research community in Austria is actually growing, and there's something happening. And then I was super hopeful, and I was talking to them a lot. I was also involved in like founding this early career researcher community in Austria, which is called AFEX Austria. So it exists since 2 years now, I think. And I was part of like founding it and doing like the first events, and it was a lot of fun. But then I also realized, okay, now I spent it half a year here, and I did a lot of stuff. It was amazing, but I actually didn't earn a cent. And then I thought, it cannot go on like this. And there were no positions for me, or no positions that I wanted to apply for in Austria at that time. I hope that changes in the future, to be honest. But I think we are on a good way. But then I was looking up different institutions, and of course I was looking up Alfred Wegener Institute, which is like one of the institutes for polar marine research on our planet, actually. And it happens to be in northern Germany again, where I also did my master's. So this is really a hotspot for marine sciences and also for polar marine sciences. And they had like this Inspires call. This is like an institute intern funding program for a lot of PhD and postdoc positions. I didn't even know that there is a call with so many positions at a time. And I just opened like the application website and there were, I think, 25 PhD positions. And I thought, okay, this is crazy. And like 10 postdoc positions or something. Then I was scrolling through all of them just for fun because I actually knew that I don't want to do a PhD. Because I have to be honest, I heard a lot of horror stories from colleagues, unfortunately, about bad supervisions or about pressure or about like a very bad work-life balance. And I was scrolling through all of them, and nevertheless, the topics were so exciting, all of them, that I thought, oh my gosh, I think I need to at least try to apply and maybe get to know the group and also talk to other PhD students about the supervision and the atmosphere in the group. And I mean, if I get an interview anyways. And then I applied for this position for was from the topic my dream position, but it has nothing to do with biology. I mean, in the broader sense, yes, but it was more a link between physical oceanography, so physics in the ocean, and geochemistry. So also element cycles, but more related to the ocean floor. And I thought, I don't know if I'm qualified for that, but it is my dream topic. And my former supervisor also said, the woman supervising this position is amazing. And then I thought, okay, I at least need to try. In the end, I got the position. And for everybody who is thinking of attending a PhD, I mean, you have to have luck, I have to say, but there is a lot of luck. I mean, I don't know if it was a coincidence, but I feel like I had a lot of luck in my life, or maybe there are more opportunities than we know. We just need to take them. But also, of course, a little bit of luck. And now I'm having this position about carbon exchange and ocean ventilation along the East Antarctic margin. This is how my position is called. And I'm in the working group geochemistry at AVI. AVI, first of all, I mean, gives you crazy opportunities to work on. It's a huge institute really focusing on polar marine research. They also have a few other branches, but the main focus is polar research, which is amazing because you are surrounded by so many people doing the same thing, being interested in the same stuff, complementing your work, which is amazing for the progress. And I really have to say that I was super lucky with my working group. So for now, I'm in my PhD now for a year, and I almost only made super good experiences. So completely the opposite of what I was what I was expecting. So the atmosphere is amazing. There is no kind of competition I was facing yet. The opportunities are amazing. My supervision is amazing. And I don't know if this is also luck. I don't know. But it at some point it gets like, I think it also maybe depends a little bit on the way how you actually see it and what you make out of it. But now I have a really nice PhD position in all kinds of ways, and I'm super happy. I'm not stressed. I have a nice work-life balance. I'm working on this amazing topic. I just came back from the Arctic, so I also, like you, I also have these super nice opportunities to go on field work. Yeah, that was a very long answer. I'm so sorry. I don't even know what the question was.
It's all right. I don't remember neither. I scrolled through a couple in between because you were answering all of them already. So it's good that you just went through the questions on your own. This is actually, but it's amazing what you have learned also in Austria. Short answers. No, it is good because my voice is not all the way here. It's just great that you're talking. That was also very interesting what you were saying. Also what you did in Austria and Graz, and now that you have this really nice PhD position, it's really cool. And you get to go to the Arctic. I hope maybe sometime you will also have to go to the Antarctic. Since you're not in there. I'm sure that would be great for you too.
I hope so too.
And as you said, your PhD focuses on the East Antarctic margin. What makes this region especially interesting or important to study?
Mm, First of all, that it's very little explored. So, I mean, in general, Antarctica is very little explored if we take it into reference with other areas on our planet. But for a very long time in Antarctic research, I would say the West Antarctic was the major focus because there you have these huge ice sheets, like these huge ice shelves, which are affecting the ocean in a very large way, and which are also kind of destabilizing, so melting down very quickly, breaking off, and dispersing. And people for a very long time thought that Eastern Arctic is kind of like the sleeping giant. So it's kind of stable and there is nothing really happening. But a few years ago, or the last decade, I think people actually discovered that there is a lot of stuff happening. So if we talk about because my PhD is embedded in the campaign East Antarctic ice sheet instabilities. So like how the East Antarctic ice sheet gets more unstable, which is actually because of ocean currents, like not just, but a major part is just of ocean currents. And this is also something I think when the poles are being researched, that people look at these huge ice caps. What is going to happen with them? This is like also a major link in all of the climate predictions and everything. And they actually thought that the Eastern Arctic ice sheet is kind of stable, at least compared to the Western Arctic. I think, which is why there was not so much research done about it. So we are lacking a lot of data. And there were assumptions that have been holding for decades, which are actually not true. So we recently discovered that there is a lot of change, which is why this campaign was also happening, the Eastern Arctic Ice Sheet Instabilities campaign, that was connected to 3 cruises of the research vessel Polarstern. This is the German research icebreaker. Maybe also some people have heard of it. And they tried to investigate over 3 cruises what's actually happening there. Like how is the ocean changing? How is the ice edge changing? How is also the biology, the ecosystems changing? What is going on in the atmosphere? Like all kinds of stuff they tried to cover in these cruises. And of course, I think this is something I cannot confirm, but I think I also heard from people that this is also a region which is less easy to access, in general for humans. I think the ways are longer, maybe, I don't know, but I think I heard from people that it's also logistically a little bit harder to actually go there. Maybe also because the most of the money was actually spent on campaigns for West Antarctica. So I think the major reason is we're lacking a lot of data, and there's actually much more happening than we thought, which is why it's very important to investigate East Antarctica. And I mean, East Antarctica is huge. There is a lot to investigate and a lot of data missing.
And Pritz Bay plays a central role in your work. Can you describe what's happening there in a way that people can picture?
Pritz Bay is actually, it is some kind of a huge bay in East Antarctica, and also some of the hotspots for East Antarctic research at the moment, because it is linked to the Emery ice shelf, which is one of the 4 biggest ice shelves in Antarctica. And this area is very important because here we have like a huge surface of ice which is connected to the ocean. And this is also why Antarctic marine research is also so interesting for physical oceanographers, like on the shelves and on the margins, because we have these ice masses that are connected to the ocean and obviously also changing like physical properties of the ocean, because when the water gets in contact with ice, it kind of gets colder. There are their temperatures are changing, but obviously also the salinity, so like the salt content, is also changing depending of if the ice shelf is melting and introducing more fresh water to the ocean, or vice versa. We have a lot of sea ice production because of the very cold water, and therefore this is maybe a little bit too scientific now. We have brine rejection because when sea ice forms on the top of the ocean, it cannot contain the salt. So the salt kind of gets strained out of the sea ice, which is called brine rejection. So this is also something funny. Every time sea ice forms on the ocean, it releases salt into the ocean, and the ocean layers beneath actually get more salty. So there's a lot of stuff happening from a perspective of a physical oceanographer. And in Pritz Bay, we have, as I said, one of these 4 big ice shelves, the Emery Ice Shelf. And they recently found out, so a few years ago, that this area produces super dense shelf water. So water that is very heavy and that sinks down to the bottom of the shelf and actually kind of flows over the continental slope down into the deep ocean, like into the very deep ocean, like thousands of meters. And this is also why Antarctica is so interesting for like our whole planet and for carbon cycling, because in this region where these ice shelves are in contact with the ocean, there is the potential to form this super dense shelf water because of the physical properties, because of high salinities due to ice formation, and also very cold temperatures because of this ocean ice interactions. So we have high salinity, low temperature waters which are very dense and very heavy. And you can really imagine it like as a own water mass that kind of isolates from the rest of the water body, and really sinks down to the bottom and flows into the abyssal, so into the very deep ocean. And this is what we call deep water production. And they used to think that there are these 3 main sites in Antarctica that are able to produce these dense shelf waters that ultimately form these deep waters. But then they discovered that Pritz Bay is actually a 4th site of deep water formation. Or at least it has the potential to be a 4th site of deep water formation. And this is why it's super important, because that kind of fuels our global ocean circulations. Like we have these overturning circulations where water flows like through all of the ocean basins, like in a vertical movement, the thermohaline circulation. And these deep water formation sites are actually the engines for our global ocean currents. And these water masses, which can be super isolated, as I just said, can also contain, for example, carbon. So if in this region we additionally have a very high potential to take up carbon from the atmosphere, bring it into that dense water mass and contain it there, this water mass actually has the potential to transport the carbon down with it into the deep ocean and store it there. That was also the thing I was talking before about when I was talking about Chile, that we have like this biological carbon pump where the carbon gets taken up from the atmosphere and then transported down by the biosphere. And now we're talking about the physical carbon pump. So we have the biological and the physical carbon pump. And in the beginning of my career, I was dealing with the biological carbon pump, and now I'm more into the physical carbon pump. So I am looking into how the water masses themselves can actually transport this carbon just because of density differences. These water masses, you can really if you look at CTD profiles, where this is a device that goes down with a lot of sensors and that constantly measures temperature, salinity, temperature, conductivity, from which you can derive salinity. Don't want to say anything wrong. And oxygen, and also other parameters. You can attach basically any sensor you want. And usually when you sit on the ship and you deploy these sensors into the water, you can live stream what they are recording. And then you see a profile on a screen, and all of a sudden, for example, the temperature goes down quite normally at a maybe, let's say, 5 degrees or something. And then all of a sudden, there is like a drop, for example, to 2 degrees. And that happens within a few meters. And this is, for example, when we change from one water mass to the other. So you really see on these profiles that these water masses are isolated from each other. And they have the capacity to store elements and transport them with them. This, of course, applies to any element. But in my case, I'm very interested in carbon, because this is one of the major elements linked to climate change, obviously. And this is why Pritz Bay is so interesting, because they recently discovered that there is this water mass and the potential for it to take up carbon and transport it into the deep ocean, which means removing it from the atmosphere. And the rest you can imagine. It's good.
You study warm, deep water entering the continental shelf. Why does this matter for ice shelves and the ocean around them?
Yeah, this is a very important question when we've already been talking about Pritz Bay and this deep water formation. Because, of course, in the beginning I said East Antarctica is very interesting to study because a lot of changes there, like the destabilization of the ice sheet, which is mainly caused by these deep, warm water masses you were just talking about. So what actually happens, and what scientists thought before, so the previous assumption was that East Antarctica is kind of isolated from these warm water masses. I mean, we need to set some ranges. If we talk about warm water masses, we talk about a water mass that is 1.0 or 1.5 degrees. So this is warm considered. This is considered warm in Antarctica. Because it's way above the freezing point of marine water. So these warm water masses were believed to be isolated from the continental shelf of East Antarctica, but because of recent changes, or not so recent changes in ocean currents, they kind of have the possibility to actually move closer to Antarctica and also even intrude onto the shelf. They already discovered that in a larger extent in Denman Glacier. This is a glacier system which is right next to Pritz Bay, actually, and there you really see the impact of these warm water masses. So the warm water basically intrudes onto the shelf. There is an upwelling, which means this is an upward flowing ocean current that flows up along the continental shelf and then intrudes the shelf and even reaches the ice shelf fronts. And now we have these 1.0, 1.5 degree warm water that reaches the ice shelf and causes it to melt. I mean, it's hard to imagine that ice melts at 1 degree temperature, but I mean, it is like this. It's not beneath the freezing point. So these kind of warm water masses reach the shelf and start to melt them down from beneath. So this is called basal melting. So the lower part of the glaciers in the glacier cavity gets to be melted away and destabilizes the upper parts of the glacier, and that also causes glaciers, for example, to calve. So you always see in documentaries these pictures of huge chunks of ice breaking down from glaciers, falling into the water, and this is also what happens there, that the glacier itself gets destabilized by these warm waters, melting it down from beneath, really carving out this glacier cavity, causing these big holes. And if that also could happen to the Emery ice shelf, so to this huge ice shelf in Pritz Bay I'm investigating. I think for now it's not happening in that extent. So Denman Glacier, the glacier next to it, is more exposed to the open ocean, which is why it's happening in a bigger rate, in a way bigger rate there. But these warm water masses are intruding more and more onto the shelf with weakening currents, also caused by climate change in a further sense. And also eventually going to reach this Emery ice shelf. And maybe they already started to melt it down, but we don't have it's really hard to make ultimate assumptions because we're missing so many data, as I just told you. So I won't elaborate on that. But this is the concept behind it. These warm water masses intrude onto the shelf, melt down these ice masses, which break down, and in the end, this destabilizes the whole East Antarctic ice sheet, because these glacier fronts are kind of holding the ice sheet back if they are stable, also combined with sea ice, which is pushing back. But if these gateways, these glaciers, these calving fronts break down, you can kind of imagine it to be like a cascade. So these gateways break down and the rest of the ice sheet slips behind it. So it's hard to imagine that this big ice sheet is kind of depending on these rather smaller glacier fronts, but they are kind of stabilizing everything. And this is why, it's really important to get more information about that, so we have an idea about the extent of these processes and about the speed of these processes, because we don't know yet. And this is what we call the modified circumpolar deep water. This is a very well-known term now in Southern Ocean research, because it is a hot topic, as I just said. And this modified circumpolar deep water is this warm water mass we're talking about, causing this ice shelf melting and the destabilization of the whole East Antarctic ice sheet. I mean, the same as happening in the West, but also in the East, which we weren't aware of a decade ago.
And is it thought that these warmer waters had been existing for a long time, or where are these all coming from? Is it all sudden, or has it been a long time? I know the research is not going on for that long as in other oceans, which are easier accessible, but what is known about it?
Yeah, I mean, these warmer water masses, they exist all over the planet. So they basically fill up our ocean basins. But since at some point they started to intrude near the continental margin of Antarctica. They were isolated by very strong circular currents, for example, the Antarctic slope current, very strong currents going around Antarctica in both directions. But these currents are weakening, which is why this physical barrier gets unstable. And these warm water masses, which fill up all our ocean basins, are actually able to intrude and move southward or northward. We actually have the same problem in Greenland. This was also one of the major topics during my past cruise in northeast Greenland, that we also have warm, deep water masses that start to move into higher latitudes and melt down glaciers from beneath. So this is a problem which we can find at both poles. But for Antarctica especially, we had this very strong physical barrier by these circular strong currents, which recently weakened, and therefore, this barrier got weaker, and these water masses can push in and even get onto the continental shelves. But they've been there all along. Yeah. I mean, it definitely also has to do with, this is also an example again of the very strong coupling between atmosphere and ocean, because we are talking about deep currents, but also surface currents. And these surface currents around Antarctica are caused by winds. So we have this very stabilized wind, these very stable wind belts all over our planet in these different climate zones. And these wind belts are also kind of starting to get unstable, also because of a changing climate. And for example, these westerly winds, which are kind of driving the Antarctic circumpolar current, it has to do. It definitely has to do with like this decoupling a little bit of atmosphere and ocean. So it's always this exchange processes. Winds change, ocean currents change, and this is the major reason. But like the patterns, how it looked in past glacial times, I don't know, but it always varies. And now we are in a period again where these systems weaken. Yeah.
And as you said, you just came back from the Arctic, and the Arctic is warming almost 4 times faster than the global average. From your perspective aboard Polarstern, what changes did you observe in Greenland waters that best illustrates this Arctic amplification?
This is actually funny because I actually saw a lot of ice. Like, I saw the opposite I was actually expecting. So I went there. Usually, when I went to Greenland the first time, I remember I was shocked because the whole Greenlandic coast was brown and green. I didn't see ice, I didn't see snow, but that was in Southeast Greenland. And now when we went up to Northeast Greenland, so really to the northern tips, because we wanted to investigate a current going there, going along the coast and also the fjord systems. It was full of sea ice, very thick sea ice. And we had a sea ice specialist who was also completely amazed and never seen such big sea ice. It was 4 meters thick at some points. And if you go there and see this, it is crazy because it is the opposite what you were actually expecting. But then I was talking to a friend who was simultaneously on Kronprinz Haakon, which is a Norwegian research vessel, and they actually had a trip to the North Pole. And it was for Kronprinz Haakon is not a strong icebreaker. So usually this ship needs support to get to the North Pole. For example, by Polarstern. Polarstern can also break through thicker ice. But this was, I think, the first time in the history of Kronprinz Haakon that it reached the North Pole without assistance of another ship, because there was almost no ice. And they went up to the North Pole. So I may be having a hard time talking about stuff I actually saw that underpins Arctic amplification. But a friend of mine on the same time went up almost to the North Pole, and they mainly went through open water. So it had to do, I'm still not sure if they know what actually happened, but it has to do something with like changing wind and ocean currents again, pushing most of the ice into one direction, I guess, and accumulating it there, while large areas of the rest of the Arctic Ocean were ice-free. And this is crazy. So really, for the first time this summer, this ship made it to the North Pole without any assistance. So they definitely saw signs of Arctic amplification. But this is also what's giving scientists a hard time, that it gets more and more unpredictable. This is also what people sometimes say, yeah, there's no climate change because we had like these huge temperature drops and these ice storms, and in New York people cannot go outside of the house because they have minus 20 degrees all of a sudden, and we never had that. And this is not because like we don't have climate change, but this is because we have climate change. I mean, we always have climate change. Climate is always changing, but this is now why we have like this fast climate change caused by anthropogenic influence, which destabilizes all kinds of weather conditions. And this makes the whole system so unpredictable. At some point, it can be super hot or super cold, and you don't know when, what it's caused by. And this was the same for us. We went into this area and we had a lot of thick ice, and we also got stuck in the ice. We were late actually going back to Germany because we were kind of frozen in. There was no way for us to go out. We could not go back. We could not go forth because the ice conditions were so extraordinary. And I think they're still having a hard time explaining this. Yeah, but this is definitely something which also indirectly shows us Arctic amplification. But from a logical point of view, you would think like, okay, you go there and there's probably not a lot of ice or less ice. But I went there and there was so much ice, while in other regions there was no ice at all, where it has been the years before. So everything changes in a very unpredictable way, and I think this is probably also the best way of showing or of describing Arctic amplification and anthropogenic climate change. That, yeah, you cannot really I feel like you cannot really expect something and see it if you go somewhere, because it can be completely different. Yeah.
It definitely sounds quite strange, but as you said, I think you can see that all over the world, that the climate is just different as it was and is changing. And it definitely sounds quite a bit terrifying to get stuck in the ice hook of the ship, not knowing when you can get out. That sounds a bit stressful. How do you handle situations like that, or how is it anyway to be on a big research ship in the Arctic?
So specifically that situation, I enjoyed it a lot. I feel like, but I may be a little adrenaline junkie. But I thought like, this is so nice, just being exposed to nature. I just like the feeling to see that we're so small and nature is so strong and we cannot do anything about it. This still kind of gives me a good feeling, like nature is still kind of in control. I don't know if you kind of can understand what I mean, but I think this situation was very interesting, and I feel like I'm not having a stressful time as long as I see like the people operating the ship are also still calm, and they have plan A, B, C, D, whatever. They have a lot of plans and they've been doing this for decades. So I really have a lot of trust in these people operating the ships, and if you see they are calm and they're proceeding with work, then yeah, I'm fine, and I'm just enjoying the view of ice on the deck. Went out for like a Feierabendbier, like a beer after work, and enjoying the possibility to see sea ice still. So this was actually quite a calm moment, because if you're stuck in the ice, there's nothing. You don't hear anything besides some cracks sometimes in the ice, because obviously it's still moving all the time. And the ship also sometimes amplifies this noise. But in general, it was a really calm and peaceful moment, in my opinion. Just being there, being exposed, enjoying the privilege to be able to see that, and also not to work, because if we're stuck in the ice, there's one time where we cannot work and we can actually relax for months, because times on ships can be really stressful, because you want to make out most of it, obviously, because this is like a very also logistically difficult operation. It takes a lot of time, it takes a lot of resources, and that's also something people really need to talk about, that it's not nothing. If you go with such a research vessel, it costs a lot of money, it takes a lot of fuel, which is why it needs to be carefully planned, and most of the time needs to be really used in an efficient way, which is why working on a research vessel can be very exhausting. But these moments in between, where you find a little bit of like calmness, make up for everything.
Okay, good. Yeah, I guess as long as the crew is calm and knows what they're doing and they have backup plans, it's fine.
I think it's the same as on a plane. If you see people up there in the plane is still like calm, you're also like, okay, we're not gonna die.
Yeah. And I can imagine that like the research is being stressful as you have like this certain time where you have to like get all the samples you want or all the research you want. It's the same when I'm going somewhere to film. I have to get all the shots I need in that specific time. So I definitely can relate to that.
Especially for that cruise, it was very interesting because I've been on some research cruises, but this was the first research cruise in ice. So this was my first research cruise on an icebreaker. I've been on ice margin ships where they can handle like some bumps by some small icebergs or stuff, but they cannot actually break ice. So we travel along the ice margin. But this was my first cruise actually in sea ice and breaking sea ice. And that makes everything even, I mean, it has pros and cons. It makes it more flexible, which also gives you a lot of room for opportunity, but it also makes it more spontaneous, and you need to be on alert always because the sea ice conditions change every day. So you cannot really plan what happens tomorrow. You can, as I said, you can have plan A, B, C, but you don't know if you wake up or if you have to sample in the night if it's actually gonna be like this, because sea ice makes everything unpredictable. And I wasn't aware of that, because when I usually go to research cruises, there is like a research program. There are stations where we're doing our program, where we are taking our samples, and they already have days assigned. So on this day, we're going to be at this station doing this, and then this, and this, and this. And this is like determined before the cruise. And during this cruise, we had our first science meeting on the first evening, and the expedition leader also said, yeah, okay, see you tomorrow. We're going to have these science meetings now every day at 7 p.m. or 7:30, I cannot remember, 7:30. To discuss the program of the next day. And I thought like, is it a joke? We're gonna have a meeting every day, like, and the meetings take quite some time. And I thought, we cannot have a meeting every day. That's so much effort. But turned out that he was serious about that because I just didn't know that. And I wasn't taking that into consideration, that sea ice changes everything. It changes the whole plan. You can also go to sleep and then maybe they call you at night and then they are, hey, sorry, we needed to skip the last station. Yours is now. Or, hey, we had open water, so we traveled like triple the speed we were expecting to. So we are already here. So you need to get up now. Or we stand up in the next day on the morning and we go to the morning meeting and they say, okay, the whole plans for today are canceled because the ice is too thick or the ice is too unstable, because we also had days where we're going onto the ice. Like we were kind of looking for ice flows where we can attach, and then the whole scientific team was going onto the ice from the ship doing sea ice research. And then it could also happen that in the morning the people said, no, we didn't find a proper ice flow. To do that. So everything changes the whole time. And this makes it, I think it really depends on your type of person. For me, I think I really liked it because that flexible way of working also opened up a lot of opportunities. Because they didn't have like a plan that was set in stone before, but the changes could have been made all the time. And we had an amazing expedition leader. I also just could go to him and ask him, hey, could you maybe imagine that we stay here a little longer and I do this and that? Or can we maybe add 1 or 2 more stations to this section? And it was always like, of course, I'll write it down. If the situation fits, we do it. And this really opens up also a lot of opportunities if you take it. On other cruises, if the plan is set, there's not a lot of room for flexibility. So I actually preferred this way of doing research. It was also kind of stressful because you never know what's going to happen and when you best go to sleep to catch the most amount of sleep you're able to. But in terms of research, you could really adapt to the environment, and that makes the research also more interesting, I think. If you see something changing conditions, or if you rethink like sampling strategies because of samples you already took, and you still have the possibility to change something on board, everything gets a little bit more intuitive, and I really like that. So this kind of research cruise was actually, I think, more my type of working.
Yeah, it sounds like it has a couple of pros in it. And you use radiocarbon as a tool in your research. How does radiocarbon help you track carbon in the ocean?
So radiocarbon is basically an isotope of carbon that is radioactive. So it's not stable, it decays over time. So it basically vanishes over time, turning back into an element it has been before. So radiocarbon develops in the atmosphere because of cosmic rays hitting an element and transforming it into another element. I didn't even know before that is possible, to be honest. I just read about that when I was applying for the position. I didn't know that elements in our atmosphere can change completely, like from nitrogen to carbon, because of the impact of cosmic rays. So we have these elements, this radiocarbon, that develop in the atmosphere with a lot of high energy input, but they are unstable. So they decay over time again back to nitrogen. But as we already have heard, carbon, for example, in the form of CO2, doesn't just stay in the atmosphere. It can also enter the ocean. So carbon basically can move through all the spheres on our planet, through the atmosphere, through the hydrosphere, so our water, through the geosphere or the lithosphere, so our Earth, basically our Earth crust, our Earth mantle, the biosphere, our bodies. It can move through everything. And one tiny fraction of this whole carbon pool is always radiocarbon, to some certain extent, if it hasn't decayed. So basically, the radiocarbon, which makes up a tiny fraction of all the carbon in our atmosphere, enters the ocean, for example, via the physical carbon pump or the biological carbon pump. It enters the ocean always via the physical carbon pump, but it can then be implemented into the biological carbon pump, for example, by plants taking up the carbon and using it to produce organic matter. So this fraction of the radiocarbon stays. So we usually have, let's call radiocarbon 14C. This is just like the number, the radiocarbon number. So we have 14C isotopes, 13C and 12C. And we always have different fractions of these different carbon isotopes in a water sample. And a water mass can actually age. This is something that sounds really abstract. And we can track that with radioactive isotopes. So for example, with radiocarbon. So if a water mass is very young, or if it gets born, this is not a scientific term, but let's say a water mass gets born the moment it is in contact with the atmosphere. Because radiocarbon can just enter the ocean via the atmosphere. There's no other way. There are maybe some teeny tiny processes, but we can neglect them. So let's say radiocarbon can just enter the ocean via the atmosphere. And so we basically assume that the ocean and the atmosphere are in an equilibrium. We assume that. So we have the same amount of radiocarbon in the atmosphere as in our upper ocean layer. And then, for example, we have this deep water production I've been talking before. The water mass gets denser and sinks down, and it actually takes this fraction of the radiocarbon that it took up from the atmosphere down with it. So usually you would think that if you go deeper in the ocean that you get just less radiocarbon because it decays from time to time. But then we have the water masses. The water mass can transport radiocarbon, for example, immediately from the surface down to the deep ocean, dragging it with it. And during that process, the radiocarbon decays, so it kind of vanishes. And if we look into a water sample, and we see that this amount of radiocarbon is left, we know that it has seen the atmosphere last time 1,000 years ago. Because when it has seen the atmosphere the last time, it must have had that amount of radiocarbon. And during the last 1,000 years, there's a certain amount that vanished because it's unstable, it decayed again. And so we kind of can calculate back when it has seen the atmosphere the last time. So basically a water mass ages if it gets into bigger or it moves away from the atmosphere. So water mass gets born when it's in the contact with the atmosphere. And the longer it has been isolated from the atmosphere, the older it is. I think this sums it up. Yeah. Yeah.
And how does the lack of direct measurements in Antarctica affect climate predictions? You also studied sediments and tiny organisms on the seafloor. What stories can they tell about the past oceans?
So the lack of data in Antarctica affect climate predictions in that way that Antarctica is a major link in, for example, global carbon cycling. And we have a lot of models and model predictions for Antarctic ocean systems or ice systems. But the model is the better, the more data we feed it, obviously. The same with machine learning. This is why we actually need data to ground truth these models and to improve these models. And I mean, in the end, some single data points you collected by yourself on a research cruise won't make up for the difference. But a lot of data points that can be used to optimize models, that makes a difference. So we need a lot of in situ data to feed models to be more precise. And this is, and these models then set the base for climate predictions. So I think this is why what we do is very important, because we already have a lot of model predictions, and to some extent they are also really good. But we still need a lot more data to ground truth them and also to improve their precision. So we actually know what we're talking about.
And how do changes near Antarctica connect to the rest of the world's ocean? You've worked in many different marine environments. How does polar research change your perspective as a scientist?
Changes near Antarctica influence the global ocean. The first thing that comes to my mind is because of the Great Ocean Conveyor Belt. So these ocean circulations that move through all our globe, through all the oceans, which are fueled by these deep water formation sites I've been talking about. So around Antarctica and also in the Arctic, we have these deep water formation sites that kind of fuel all ocean circulations. So I think this is the most understandable way why Arctic Ocean and the polar oceans influence the whole globe. They carry elements, they carry heat, they carry energy in all kinds of forms. They also carry biological information. And these oceans that carry all of the things I just mentioned, they basically kind of start in the polar oceans, to formulate it better, they get fueled by these areas in the polar oceans that drive this deep water formation. So I would say this is the connecting point to all the ocean currents on our planet. And you asked what was the second question?
How does polar research change your perspective as a scientist?
It changed my perspective as a scientist that I think we need to be way more open-minded when we pursue science. So I feel we, especially in polar regions, we deal with such big systems and processes that we really need to think interdisciplinary. And I mean, this is in general the approach everybody should go for, because first of all, because it's a lot of fun to work with scientists together from other fields. And also, it's way more serious because our nature is so complex. You can't just like look at it from one point of view, from biology or physics or chemistry. And I think polar oceans have once more showed me that it's super important to work with other fields together, because processes are so big and complex that we need everything to explain them, and it's still not enough. So they taught me that I feel even smaller, and that there is still so much more to do and discover that I thought, and that everything is connected. Yes, that everything is connected. I think this is also the major lesson.
And for the last question, if listeners should remember one thing from this conversation, what should it be?
I think actually the last thing I said, so that everything is connected, but that everything is connected. And I think that maybe applies to kind of everything, that we need to be a little bit more open-minded, making assumptions, talking with other people about it, exchanging different experiences, look at problems from different point of views. And I think it's also very important, because I've been talking a little bit about my path of career, is to encourage each other. Don't work as competitors. This will make you unhappy and will maybe lead you somewhere, but at some costs. So I definitely found out that my way is to work in a team, to work together, to appreciate skills from other people, and to appreciate it that you're surrounded by them and can learn from them. And you can also give something back. So I guess from a scientific point of view, everything is connected. We still don't know a lot. And I think from a personal point of view, encourage each other, just try things out, work together as a team, and appreciate that we are able to do so. That makes work even nicer.
Well, thank you so much for sharing your research and the work you do in the podcast. I hope to have you on the podcast sometime again with your newest research. And it was a pleasure talking with you and learning about all the things you do in your research.
Yeah, thank you very much. And thank you for the amazing questions. I also really enjoyed it.